in the literal sense of orbital mechanics. Venus doesn't spend most of its time on the far side of the Sun from Earth. It's been hiding in plain sight, visible to the naked eye. The brightest object in the night sky after the moon. So bright that it casts shadows on clear nights. So familiar that ancient civilizations named it after their most important deities, Ishtar, Aphrodite, the morning star, the evening star, a planet that human beings have been observing, naming, worshiping, and studying for at least 5,000 years. And in all that time, through all those millennia of observation, through 400 years of telescopic astronomy, through the space age and the first flybys and the Soviet landers and the Mellon radar mapper, we fundamentally misunderstood what we were looking at. We thought Venus was an alien hell, a cautionary tale, a world defined by its failure by the runaway greenhouse effect that turned what might have been a pleasant world into a pressure cooker where the surface temperature is 465 degrees Celsius, hot enough to melt lead with a surface pressure 92 times Earth's and an atmosphere of sulfuric acid clouds that blocks every view of the surface from orbit. The anti-Earth, the place that evolution went catastrophically wrong, the nightmare version of what our planet could become. This picture is not false. The current Venus is all of those things. The atmosphere is genuinely lethal. The surface is genuinely an inferno. The greenhouse effect is real and extreme and serves as a genuine warning about what unchecked atmospheric warming can do to a rocky planet. But here's what the picture missed, what it systematically, persistently, consequentially missed. The current Venus is not Venus. It's what Venus became at some point in its history after a transition that the evidence suggests was neither inevitable nor ancient. The current Venus is the end state of a planetary evolution. That began with something dramatically different. The beginning was a world that looked in all the ways that matter for habitability remarkably like Earth, same size. Earth's radius is 6,371 kilometers. Venus's radius is 6,052 kilometers. The difference is less than 5%. For comparison, Mars' radius is 3,390 kilometers, barely half of Earth's. Venus and Earth are twins. In the catalog of planetary sizes across the solar system, they're virtually indistinguishable, same mass. Earth's mass is 5.97 times 10 to the 24th kilogram. Venus's mass is 4.87 times 10 to the 24th kilogram. Venus is 81.5% of Earth's mass. Again, for comparison, Mars is about 10% of Earth's mass. In terms of bulk gravitational properties, the strength of the surface gravity, the ability to retain a thick atmosphere, the geothermal heat generated by radioactive decay in the interior, Venus and Earth are nearly identical. Same bulk composition. The density of Venus is 5.24 grams per cubic centimeter. Earth's density is 5.51 grams per cubic centimeter. The difference is about 5%. Consistent with the two planets having formed from the same mix of rocky and metallic material in the same region of the protoplanetary disk, with nearly identical proportions of iron, silicon, magnesium, and oxygen, same formation epoch. Both Venus and Earth accreted from the protoplanetary disk approximately 4.5 to 4.6 billion years ago in the same general region of the inner solar system. Venus at 0.72 astronomical units from the Sun, Earth at 1 astronomical unit. They're separated by less than 40 million kilometers at closest approach, closer than any two major planets in the solar system. Same initial endowment of volatiles. The same comet and carbonaceous asteroid bombardment that delivered water and organic chemistry to Earth also delivered it to Venus. Both planets received essentially the same chemical package from the early solar system. Water, carbon compounds, nitrogen, the building blocks of both atmospheres and oceans, and potentially life. Venus and Earth are as similar as two planets can be. They're not just neighbors. They're siblings born at the same time from the same material with the same initial conditions. And one of them became a paradise for life and the other became hell. The question that is now driving one of the most exciting programs in planetary science is now driving one of the most exciting programs in planetary science. Science is, when did Venus become hell, and for how long before it did? Was it something else? Let me take you to the specific scientific evidence that has transformed our understanding of Venus's history. And that has led a growing number of planetary scientists to conclude that Venus was not always what it is today. The case begins with water. specifically with the deuterium to hydrogen ratio and the small amount of water vapor that still exists in Venus's atmosphere. We've discussed the D/H ratio in the context of Earth's ancient water. The fact that deuterium enrichment is a chemical timestamp, a fingerprint of the conditions under which water formed or was processed, the same logic applies to Venus. Venus's atmosphere today contains very little water vapor, only about 30 parts per million, compared to Earth's roughly 10,000 parts per million in the lower atmosphere. Venus is extraordinarily dry, but the water vapor that is present has a D/H ratio that is roughly 150 times higher than Earth's ocean D/H ratio. This extreme deuterium enrichment is a specific and important signal. When water is lost from a planetary atmosphere, when water molecules in the upper atmosphere are broken apart by ultraviolet radiation and the hydrogen atoms escape to space, the lighter hydrogen one escapes more easily than the heavier deuterium. The remaining water becomes progressively enriched in deuterium. The higher the D/H ratio, the more water has been lost. Venus's D/H ratio of 150 times Earth's value means Venus has lost an enormous amount of water over its history. The calculation working backward from the current D/H ratio and the current water abundance, accounting for the rate of hydrogen escape, gives a specific lower bound on how much water Venus once had. The result is staggering. Venus may have had enough water to cover its entire surface to a depth of at least several meters, and possibly much more. Some models suggest the original water inventory was comparable to Earth's ocean, a global layer of liquid water 3 kilometers deep. Others give more modest estimates, but the direction is clear and the magnitude is substantial. Venus had water, a lot of water, for a long time. Now let me tell you about the climate models, because the water evidence tells you that Venus had water, but it doesn't tell you how long the water lasted, whether it was a brief early phase that ended quickly or a sustained habitable period that lasted for billions of years. This question was addressed in a landmark 2016 study by Michael Way and colleagues at NASA Goddard Institute for Space Studies. The Way team ran sophisticated climate simulations of early Venus using the same general circulation models used to study Earth's climate, adapted for Venus's conditions under a range of assumptions about the early rotation rate, atmospheric composition, and solar luminosity. The specific question was, could early Venus have maintained liquid water on its surface given that the young sun was about 30% dimmer than it is today? And given Venus's proximity to the sun, the results surprised the planetary science community. Under reasonable assumptions about early Venus, a slow retrograde rotation similar to today, an early atmosphere dominated by carbon dioxide and nitrogen with modest amounts of water vapor, and an initial ocean covering a significant fraction of the surface, the simulations found that Venus could have maintained stable surface temperatures between roughly 20 and 50 degrees Celsius for billions of years. The key was the clouds. Venus rotates so slowly one Venus day is 243 Earth days that the sun-facing side is illuminated for extremely long periods. On a fast-rotating planet, this would produce extreme heating on the day side. But on a slowly rotating planet, the atmospheric circulation develops a specific pattern of thick, persistent cloud cover over the sunlit hemisphere. A cloud deck that reflects an enormous fraction of the incoming solar radiation back to space, cooling the surface. This cloud feedback, specific to slow rotators receiving intense solar radiation, is a genuine planetary stabilization mechanism. It's not special pleading. It emerges naturally from the atmospheric dynamics when you run the models without predetermined conclusions. The clouds that would form on slowly rotating early Venus are thick enough, persistent enough, and highly reflective enough to compensate for Venus's closer proximity to the Sun. The Way simulations showed that early Venus, with its cloud-stabilized climate, could have been habitable for approximately 2 to 3 billion years. Not briefly habitable, habitable for a geological epoch comparable to the entire history of complex life on Earth. 2 to 3 billion years of liquid water on Venus. 2 to 3 billion years of clement surface temperatures. 2 to 3 billion years during which the same chemistry that was driving the origin and evolution of life on Earth was potentially operating on Venus. It's been there all along. Not the hellish Venus we see today. The habitable Venus that existed before whatever ended it, sitting in our sky, 40 million kilometers away, the brightest light in the night sky, hiding a history that we're only now beginning to understand. Now let me tell you about the transition, because understanding when and how Venus became what it is today is as important as understanding what it once was. And because the specific mechanism of Venus's transformation is one of the most consequential questions in planetary science. The current leading hypothesis involves a catastrophic volcanic event, a planet-wide resurfacing that occurred somewhere between 700 million and 1 billion years ago when Venus underwent an episode of extreme volcanic activity that released enormous quantities of carbon dioxide from the interior into the atmosphere, triggering a runaway greenhouse effect that boiled away the oceans and transformed the climate irreversibly. The evidence for this catastrophic resurfacing comes from the crater distribution on Venus's surface. Planetary surfaces accumulate impact craters over time. The longer a surface has been exposed, the more craters it has. The Moon's heavily cratered highlands record bombardment from 4 billion years ago. Mars' ancient southern hemisphere is similarly heavily cratered. Venus's surface, as mapped by the Magellan radar orbiter in the early 1990s, has a strikingly uniform and low crater density. Not the heavy cratering of ancient surfaces, not the complete freshness of very recent volcanic resurfacing, something intermediate, a surface that is uniformly about 700 to 800 million years old across the entire planet. This uniform age is inconsistent with gradual ongoing geological activity. On Earth, plate tectonics constantly recycles the crust. Old ocean floor subducts and is replaced by fresh basalt from mid-ocean ridges. So the ocean floor is never older than about 200 million years, while the continents are ancient. This produces a spread of surface ages across the planet. Venus has no such spread. The surface is the same age everywhere. The most natural explanation is that the entire surface was resurfaced simultaneously or over a geologically brief period. In a catastrophic volcanic event that buried the old surface under fresh lava and reset the crater age clock planet-wide. This catastrophic resurfacing might be the event that ended Venus's habitability. A global volcanic eruption sustained over millions of years, releasing gigatons of carbon dioxide into the atmosphere, could have overwhelmed whatever carbon cycle regulation Venus had previously maintained, driving the greenhouse effect to runaway conditions. The oceans evaporated. The water vapor in the atmosphere itself, a greenhouse gas, accelerated the warming. The upper atmosphere, saturated with water vapor, was dissociated by UV radiation. The hydrogen escaped to space, the oxygen combined with surface rocks, and Venus settled into the hellish equilibrium it maintains today. If this scenario is correct, Venus's transition from habitable to lethal was not gradual and inevitable. It was catastrophic and relatively recent, occurring in the last 20% of the solar system's history, perhaps 700 to 800 million years ago. Before that transition, Venus was potentially habitable for 3 billion years. 3 billion years is long enough for the evolution of complex multicellular life on Earth. 3 billion years is long enough for the development of sophisticated ecosystems. 3 billion years is, if the origin of life can occur wherever conditions permit, more than enough time for life not just to arise, but to flourish. Now, let me tell you about something that connects the Venus habitability question to one of the most persistently controversial observations in the history of planetary science. An observation that has divided the scientific community, generated dozens of papers, been explained and re-explained and challenged and defended, and that remains, after 5 years of intense analysis, not definitively resolved. In September 2020, Jane Greaves and colleagues published a paper in Nature Astronomy reporting the detection of phosphine in Venus's atmosphere. Phosphine pH3, a molecule consisting of 1 phosphorus atom and 3 hydrogen atoms, was detected in absorption in the ultraviolet spectrum of Venus at a concentration of approximately 20 parts per billion in the cloud layers at altitudes of 50 to 60 kilometers. The reason this detection was immediately explosive is that phosphine has a specific abiotic chemistry problem on Venus. Unlike most molecules, phosphine is not stable in Venus's highly oxidizing atmosphere. It should be rapidly destroyed by the sulfuric acid and other oxidizing compounds in the cloud layers. The only known abiotic processes that produce phosphine lightning, volcanic outgassing. Photochemical reactions produce it at rates far too low to explain a concentration of 20 parts per billion. On Earth, the only significant sources of phosphine are biological, produced by anaerobic bacteria in specific environments. The implication, stated carefully by Greaves and colleagues and with enormous accompanying caveats, was that the phosphine detection, if real, might indicate the presence of some unknown chemical process or potentially of biological activity in Venus's cloud layers. The Venus cloud layers at 50 to 60 kilometers altitude are one of the few environments on Venus where temperatures and pressures are relatively benign. Roughly 0 to 60 degrees Celsius, pressures of 0.4 to 2 bars. This is the only region of Venus where current conditions approach the range compatible with life as we know. If there is any surviving chemistry or any surviving biology from the ancient habitable Venus, the cloud layers are where it would most plausibly persist. The phosphine detection immediately attracted intense scrutiny. Multiple independent research teams reanalyzed the original JCMT and ALMA telescope data. The analyses found several things. First, the original claimed concentration of 20 parts per billion was likely an overestimate due to calibration issues with the ALMA data. The corrected value is closer to 1 to 5 parts per billion. Second, the feature in the spectrum attributed to phosphine is real. It's not an instrumental artifact, but its assignment to phosphine specifically is contested. Some researchers argue the feature could be attributable to sulfur dioxide absorption at a different rotational line. The current status of the phosphine claim is genuinely uncertain, not definitively confirmed, not definitively refuted. The spectral feature is real. Whether it's phosphine is debated. Whether phosphine at any concentration in Venus's atmosphere implies biology is itself a complex question that depends on whether any abiotic mechanism could produce it in Venus's specific chemical environment. What the phosphine debate has done, regardless of how it's ultimately resolved, is focus intense scientific attention on Venus's cloud layers as a potentially habitable or at least chemically extraordinary environment. The chemistry of Venus's clouds is complex, poorly characterized, and potentially surprising. The specific particles responsible for the mysterious UV absorber in the clouds, a substance that absorbs strongly. In the ultraviolet, and whose identity has been unknown since it was first detected in the 1970s, remain unidentified. Some researchers have proposed that the UV absorber could be biological material, microbial cells adapted to the cloud environment. These proposals are speculative, but they're scientifically motivated speculations, driven by real unresolved chemical mysteries in the Venusian cloud layers that current models can't fully explain. Let me tell you about the missions that are going to resolve these questions. Because the Venus science community, energized by the habitability models, by the phosphine controversy, by the growing understanding of Venus as a potentially once habitable world, has successfully advocated for a new generation of Venus missions that will transform what we know about Earth's sister planet. In June 2021, NASA announced the selection of 2 new Discovery-class missions to Venus. The first is Da Vinci Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging. Da Vinci will send a descent sphere into Venus's atmosphere, sampling the chemistry at multiple altitudes as it falls through the cloud layers and the lower atmosphere to the surface. It will directly measure the noble gas abundance of xenon, krypton, and argon, which encode information about Venus's early atmospheric history and how it evolved. It will image the Tessera, the ancient highland regions that may be the only surviving surface exposures of terrain older than the catastrophic resurfacing event. And it will measure the water abundance and isotopic composition at multiple altitudes, providing the most detailed D/H profile of Venus's atmosphere ever obtained. The second mission is Veritas Venus Emissivity, Radioscience in SAR, Topography, and Spectroscopy. Veritas will produce the most detailed topographic and geological map of Venus ever made, with a resolution roughly 10 times better than Magellan, and will use infrared spectroscopy to map the surface mineralogy. Mineralogy tells you about the history of water. Clay minerals, carbonates, and hydrated silicates record past aqueous chemistry. If Venus's ancient highlands preserve mineralogical evidence of past water interaction, Veritas will find it. The European Space Agency is sending ENVISION, a Venus orbiter with synthetic aperture radar, infrared sounding, and atmospheric chemistry instruments, targeting a launch in the early 2030s. These three missions, Da Vinci, Veritas, and ENVISION, will collectively answer the questions that the current data can only hint at. Did Venus have a global ocean? How long did it last? When and why did Venus lose its water? What is the chemistry of the cloud layers? And does it harbor any unexplained chemistry that might indicate biological activity? What do the ancient Tessera tell us about pre-resurfacing Venus? The Venus Renaissance is underway. After decades of neglect, no dedicated Venus orbiter has operated since Magellan in the early 1990s. The planet that was once Earth's twin is returning to the center of planetary science. Let me close this first part with something that I think captures the full significance of what the new understanding of Venus means. Not just for planetary science, but for the search for life and for our understanding of what makes a planet habitable. The standard narrative of planetary habitability, the one that has shaped astrobiology for decades, places Earth in a special position, the habitable zone, the Goldilocks zone, the region around a star where temperatures are right for liquid water on a planetary surface. Earth is in the habitable zone. Mars is at the outer edge. Venus is just inside the inner edge, too close to the sun to be habitable. This narrative is wrong, or at least it's incomplete in a way that matters enormously. Venus was in the habitable zone for billions of years, not because it's inside the conventional habitable zone boundary, but because the cloud feedback mechanism provided by its slow rotation kept temperatures in the habitable range despite its solar proximity. The habitable zone is not a fixed region of space. It's a function of a planet's atmospheric composition, its rotation rate, its ocean coverage. Its albedo, a function of properties that vary from planet to planet and change over time as the planet evolves. Venus was habitable, not in the future, not hypothetically, in the past, for billions of years. And it was habitable not despite being Venus, but because of what Venus was before it became what it is today, before the catastrophic volcanic resurfacing that ended its habitability 700 to 800 million years ago. This changes everything about how we should think about habitable worlds. If Venus was habitable for 3 billion years, if the inner edge of the habitable zone is further in than the conventional model suggests, then the number of potentially habitable worlds in the galaxy is larger than we thought. Planets closer to their stars than previously considered habitable might have the same cloud-stabilized climates that made early Venus clement. The habitable zone is wider than the textbooks say. And here's the implication that I find most striking. If Venus was habitable for 3 billion years, if it had liquid water, clement temperatures, and the same chemical prerequisites for life that Earth had, then the probability that life arose on Venus is comparable to the probability that life arose on Earth, maybe lower if Venus's geological activity was different in ways that affected the specific chemistry of the origin of life, but not zero, not negligible. There might have been life on Venus. Simple microbial ancient life living in the oceans of a world that no longer exists, in the lakes and rivers and hydrothermal vents of the habitable Venus that preceded the inferno. A biosphere that flourished for billions of years and then ended abruptly, catastrophically, completely when the volcanic resurfacing triggered the runaway greenhouse that destroyed the surface environment. If that life existed, if Venus had its own biosphere for 3 billion years, where did it go? Most of it died when the surface became uninhabitable. But some of it, the most hardy, the most adaptable, the organisms that had colonized the upper atmosphere as secondary environment might have survived, adapted to the increasingly hostile conditions as the surface was destroyed, retreated upward into the cloud layers as the surface temperature climbed past 100 degrees. Past 200 degrees, past 300 degrees, evolved to survive in the acidic, turbulent, UV-bathed environment of the cloud deck. It's been there all along. The second Earth, the twin planet, the world that might have had its own history of life. Its own 3 billion year biological experiment, its own answer to the question of whether life is common in the universe, sitting in our sky 40 million kilometers away. The brightest object visible to the naked eye, hiding everything it once was behind clouds of sulfuric acid. In part 2, I want to go deeper into the geological evidence for ancient Venus, into what the Tessera highlands are and what they might tell us about pre-resurfacing Venus, into the specific chemistry of the Venusian cloud layers and the unresolved mysteries they contain, and into what? The Da Vinci probe will actually measure when it descends through Venus's atmosphere in the late 2020s. It's been there all along. Closer than Mars, brighter than any star, the most observed planet in human history after our own. And we never knew what we were looking at. So we'd arrived at this place where Venus, the brightest object in the night sky, Earth's nearest planetary neighbor, the planet that has been observed by human eyes for at least 5,000 years, turns out to have been something completely different from what we assumed. Not the alien hell it is today, but a world potentially habitable for 2 to 3 billion years with liquid oceans, clement temperatures, and every chemical prerequisite for life. A world that was transformed catastrophically, relatively recently in geological terms, by a planet-wide volcanic resurfacing that triggered a runaway greenhouse effect and destroyed whatever habitable environment had existed before. Now I want to go deeper into the specific geological evidence for ancient Venus, what the Tessera highlands are, and what they might tell us about Venus before the catastrophe, into the specific chemistry of the cloud layers and the unresolved mysteries that have been accumulating since the 1970s, into what the Da Vinci descent probe will actually measure, and into something that I think is the most scientifically extraordinary aspect of the entire Venus story, a specific way that Venus's evolution serves as a natural experiment in planetary habitability that has implications for every habitable world in the galaxy. Let me start with the Tessera. When the Magellan spacecraft mapped Venus's surface with synthetic aperture radar between 1990 and 1994, it revealed a planet whose topography is broadly flat. A planet without the dramatic elevation contrasts of Earth, without the deep ocean trenches and high mountain ranges that plate tectonics produces. Most of Venus's surface sits within about 2 kilometers of the mean elevation, a gentle rolling volcanic plain with occasional large volcanic constructs. But scattered across this relatively flat surface are specific isolated highland regions that stand dramatically above the surrounding plains. The largest Ishtar Terra in the north and Aphrodite Terra near the equator rise several kilometers above the surrounding lowlands. And on these highlands, Magellan found a terrain unlike anything else on Venus. A terrain of intensely deformed, complexly fractured, heavily ridged rock that planetary scientists call Tessera, from the Greek word for tile. Because the surface looks like an intricate mosaic of intersecting ridges and troughs. The Tessera are old, not absolutely dated. Venus has no samples in Earth laboratories, no radiometric ages from return material, but relatively old based on their crater density and their geological relationships with the surrounding plains. The Tessera predate the catastrophic volcanic resurfacing that covered most of Venus's surface 700 to 800 million years ago. They're the remnants, the only surviving remnants of whatever surface existed before the catastrophe. They're the windows into ancient Venus. What are the Tessera made of? This is the question that Veritas infrared spectrometer and Da Vinci imaging system are specifically designed to answer. And it's one of the most consequential questions in planetary science. On Earth, the geological distinction between continental crust and oceanic crust is fundamental. Oceanic crust is basaltic, dark, dense, iron-rich, formed at mid-ocean ridges and continuously recycled by subduction. Continental crust is granitic, lighter, silica-rich, aluminum-rich, formed by the partial melting of subducted oceanic crust in the presence of water. The key ingredient for granitic continental crust formation is water. The specific mineralogy of granite, its quartz and feldspar content, requires water-saturated partial melting conditions that don't occur without liquid. Water cycling through the crust. If the Tessera highlands of Venus are made of granite or granitic rocks, that would be direct mineralogical evidence that Venus once had liquid water in contact with its crust.